So today we will do another problem in the dynamic programming, which is all source shortest path. So all source shortest path. Okay, and this was devised by a person called Floyd. So it's also called as Floyd's algorithm. We had done a slightly different version of it, which was single source shortest path, right? Which was actually Dijkstra's algorithm. Right? So the difference there is we used to have one source. We had to pick a source in a graph and then find all the other the path to all the vertices from this graph. That was the problem with the single source shortest path. Here it is all source shortest path. That means after solving this, from any vertex, right? Not just from the source vertex, from any vertex to any other vertex, you can find the graph. Right? It will show you the path to all other vertices. So it is all source, right? The algorithm is very simple. Just one note on dynamic programming, right? We saw in multi-stage graph also. So what dynamic programming actually does is splits the problem into smaller parts. So dynamic programming, it actually splits your problem into smaller chunks, okay? And it tries to use wherever possible the previous solution, right? Use previous solution. Right? If you look at it here, what we did in the multi-stage graph also, you remember we used to first have this cost 3.5 and later down, right? We used to always, wherever that cost 3.5 comes, we used to reuse that, right? We used to never compute this again. We used to reuse what was already solved. So that's what happens with dynamic programming. Here also we will solve some problem in the first step number 1, and wherever in the later steps, right? Wherever it is needed, we will go back and refer, if needed, the previous solution. So that's one aspect of dynamic programming. The other aspect of dynamic programming is it actually tries all the paths. It tries all possible solutions. Right? It tries to capture all possible solutions, right? And in that, it will pick the best one. Unlike greedy algorithm, we saw this yesterday, last class also. Greedy algorithm will, you pick one thing and you're done. You cannot change that, right? So you possibly pick one kind of a solution and you continue with that, right? But dynamic programming tries all possible solutions, and among that, it picks the best possible solution, right? And that is why any program with dynamic programming is pretty lengthy if you compare. If you see this, the concept is very straightforward. Like we saw that in the multi-stage graph also, right? If you see, the formula is very straightforward. One formula we need, right? You have a edge, direct edge, and what was the cost of the previous path. The formula is very straightforward, but look at this, how many times we had to run that formula, right? We saw this in the last multi-stage graph also. And now same thing is going to happen with also shortest path also. If you look at the formula, I'll run through that. This is one-liner formula, right? It is pretty straightforward, but you have to do this so many times. So before telling you what we have to do and how many times we have to do, we'll just take a look at what the formula says. So I hope this is visible to you all. Right? Okay, so what this formula states is, if you want to compute the edge from I to j, suppose I to j is your edge, and you want to compute what is the best possible minimum cost from I to j, what you can do is you can do two things. You can pick the direct cost from I to j, or see if you have something called, you can intermediate, you can go to some vertex and then reach j, right? So you go from I to k, and then k to j, right? Suppose this cost is 20, say this cost may be 5 and 5. So you have two possible options. If you go directly from I to j, your cost may be 20. If you go from I to some intermediate vertex, so k is an intermediate vertex, you get 5, and from k to j, you get 5, right? So you have to choose whatever is the minimum. right? So minimum is this, so you choose this path, right? That is all the formula is, right? So why that simple part of it, that's what you have to do. Now, how many times you have to do? Look at this. There are 3 nested for loops. For loop 1, for loop 2, for loop 3, right? So K is actually your intermediate vertex. We will do this formula, okay? So don't worry about that. K loop is for your intermediate vertex. That means if there are n vertex in your graph, right here, if you see 1, 2, 3, 4, there are 4 vertices in your graph. You will run, okay, if 1 is your intermediate vertex, how will it look? If 2 is your intermediate vertex, how will it look? If 4 is in the middle path, how will it look? If 3 is in the middle path, how will it look? So this is for intermediate vertex, right? And these two are your normal edges, I, j. Okay. So if you see, you have to run, when we did that complexity of algorithms, we saw nested loops, nested for loops, right? So this for loop takes n. This for loop will take, it is nested, so it is n square. And this is third nested, so it is n cubed. So this is the complexity. And that is why I was saying this will be pretty lengthy. You have to just do this formula, but you have to do n cube times. So what does that mean? Here, example, you have number of vertices as 4. So you will be running this steps these many times, which is what? It is 64 times, right? You have to run this 64 times, then you will get the solution, right? I just, for easy purposes, this is going to be like really long, but same thing you have to do. So I just wrote it down, so it will help fasten the time today. Even in your exams, just take a note. It's very straightforward. Like you will, you don't have to struggle to solve this problem. The problem solving is very simple, but it's just that you have to make sure it takes so much time. So note down when you're practicing, note down how much time it will take for you. So you have a rough idea. You may need like say 10 minutes or 15 minutes, depending on how fast you are, right, to solve this problem. Also, if it depends on number of vertices. So if it's a 3 vertex graph in your exam, it'll be much faster because it'll be what, 3 cube times, right? So it'll be 3 into 3 into 3. So 9 threes are 20. You will do only 27 times, right? But if it's a 5, it's going to be more. If you have a graph with 5 vertex, it's going to be more. You'll be doing 125 times. So just remember that, okay? So let's start doing this. So first we need to build an adjacency matrix, which is, I call it as D0 because this is your starting one. This is same. Look at the graph and build your adjacency matrix. 1 to 1, I put 0. 1 to 2 is 10. 1 to 3, there is no direct edge, so it is infinity. 1 to 4 is 40. So similarly, I have done this initial adjacency matrix. Okay. So now comes your step. So remember we did K. We said K is your intermediate vertex, right? So here we will be doing D1. So here, how many vertex we have? We have four vertex, right? So we'll be doing for D1, D2, D3, and D4. So what D1 means? D1 means 1 is in middle. So you have some start vertex, you have some end vertex, okay, and 1 is in middle. D2 means you have some start vertex, 2 is in middle, and you have some end vertex, okay. 3 means 3 is in middle. You have some start and some end. And D4 means 4 is in middle. Okay, you have some start and some end. Okay, so we will take a combination for all of this. So first we will do with D1. D1 of, you have to try now for all the edges. Okay, so how will you do all the edges? So this one, there are, all of these numbers are edges, right? So this one is nothing but 1, 1. So this edge is 1, 2. This edge is 1, 3. This edge is 1, 4. Similarly here 2, 1. This is 2, 2. This is 2, 3. This is 2, 4. Similarly, you have to do for this. This is 3, 1, 3, 2, 3, 3, 3, 4. And finally, you have to do for your fourth edge, which is between 4, 1, 2, 3, 4. So these are all possible edges for you, right? So how do you compute this? D1 is, we saw the formula, right? Formula says you can directly go from, if you have to go from I to J, say this is your I to J, the formula says you can directly go from I to J, or, right, you can go to some intermediate vertex K, and from there go to J, right? So here for us, we know K is 1. So we can go directly, this is this, or you can go to some intermediate vertex. Now, because K is 1 here, my intermediate vertex is nothing but 1. And from 1 to J. Okay. I will solve it till here. I mean, I will solve till 2 because then probably you'll understand. Okay. And after that, I will pause. If you have any questions, please tell me. So if you look at this again, I'll repeat. I to J can be directly from I to J. So it is 1, 2. Or you can go to intermediate vertex K. Now K in our case is 1, right? So I go from 1 to 1, and from there K to second vertex. Okay. So 1, 3 is direct, or I go from 1 to 1 and then 1 to 3. Similarly, I can go direct, or 1 to 1, 1 to 4. Okay. Let me do this also, second one. So here again, I can go direct 2, 1, or I can go to intermediate 1, and from there I can go to second vertex. So here it is direct, or I can go to 1, and from there I can go to the second vertex. So after this, I will pause and ask you if you understood this or not. Is this clear? Did you understand how this is built? Yeah. Anybody? Do you understand how we are building this? Yes, no. Yeah. Shazia, Hafsa, Taj, Seher, and others who have joined, right, together. Are you there? You're sleeping? You understood what this is? I'm not getting any answers. You guys are there? Pause. Okay. So we will first populate it and then maybe we can solve. Okay. So now we are done with 1 as intermediate vertex. We finished this. Okay. Now we need to try this with D2. D2 means 2 is my intermediate vertex. Like for example, this one, I can go from 1 to 1 directly. 1 to 1 is nothing but a loop, but for understanding, okay, let me take some other example. Let me take, say, 2, 4. 2, 4, 2 to 4, right? So here I can go 2 to 4 directly, or in D2 case, 2 is my intermediate vertex. So I can go from 2, 2, 2, 4. Okay. Let's take one more example here, 3, 4. So I can go 3 to 4 directly, or I can go 3 to 1 intermediate vertex, and then I go to 4. And we know that in this case, we are trying with 2 as our intermediate vertex, right? So obviously it is this. So here, if I have to put up, it will be 3, 4, or going from 3, 2 to 2, 4. Okay. So just one other point I want to highlight. Once you're done with this, when you're solving D1, you will be referring to the D0's adjacency matrix. That means this one. Okay, so we'll do one thing. Let's solve this. So then you'll understand how I have to do the next step. Let's solve this. We finished D1, right? So let's solve this. So what we have to do, basically by doing this, what we are trying to find out is, first of all, wherever there is infinity, where we know that there is no direct edge, like for example, 1 to 3. 1 to 3, there is no direct edge. But can I go, like for example, here, I can go to 4 and then 4 to 3. So there is an alternate path, right? So let's see if this algorithm can find that out, right? So instead of infinity, I should get some other number here. That's the intention of this algorithm. So let's try to solve this. So ideally, wherever this 1 is, it will not change much, but anyways, I will do it. It is 1 to 1, which is 0. You have to look at this D0 adjacency matrix, okay? 1 to 1 means 0. Okay. Again, here 1 to 1 is 0, 1 to 1 is 0. So this basically will not change. So basically, these values will not change. You can as well skip it. Let's try 1 to 2. 1 to 2 is again 1 to 2, which is 10. Otherwise, you can go from 1 to 1, which is 0, and then from 1 to 2, which is 10. So 0 plus 10 is also 10. So there's nothing changing here. It is the same. Let's try this one. 1 to 3. 1 to 3 is infinity, or I can go to 1 to 1, which is 0, and then 1 to 3. 1 to 3 is again infinity. So there's nothing changing here also. And finally, 1 to 4. 1 to 4 is 40. And I go from 1 to 1, which is 0. 1 to 4 is also 40. So this is also nothing changing here. It's the same, right? So the same thing I've copied here to check easily. Let's do this one. 2 to 1. 2 to 1 is infinity. 2 to 1 is infinity. 2 to 1 is infinity plus 1 to 1, which is 0. This is also not changing. Same. Let's try 2 to 2. 2 to 2 is 0. 2 to 1 is infinity. Plus infinity plus, it doesn't matter. It will be infinity only. So whichever is minimum. So it is 0 or infinity. So it is 0. Right? Here 2 to 3. 2 to 3 is infinity. Otherwise, you can go from 2 to 1. 2 to 1 is also infinity. So here also it's nothing much changing. Then let's try 2 to 4. 2 to 4 is 20. Or can I go to 2 to 1? 2 to 1 is infinity. So here also nothing much changing. It will be the same number. Okay. Let's try here 3 to 2. 3 to, we have to do this, right? 3 to 1. 3 to 1 is 50. Otherwise, I can go from 3 to 1, 50 plus 1 to 1, which is 0. It will be the same. Let's try 3 to 2. So this is the same. 3 to 2 is infinity. Or can I go from 3 to 1, which is 50, and then from 1 to 2, which is 10. So look at this one. This is interesting. This combination is actually giving you some changed value. Right? So initially we said 3 to 2, right? 3 to 2, there is no path. Let's look at the graph also. 3 to 2, there is no direct path, right? But now you can put 1 in, like here, we don't have any direct path here, but we are trying with 1 as the intermediate vertex. So then we are able to go from 3 to 1 and 1 to 2. So this, putting 1 in the middle has solved this path. So now 3 to 2, instead of becoming infinity, we said minimum of this or this, right? So now it will become 60. So this has changed, right? Your value has changed in the graph. So instead of infinity, there is some value here. So let's try this. We said, see, diagonal values will not change. Okay, so we can skip this altogether. I'll skip this. It will be 0 only. 3 to 4. 3 to 4 again is infinity. Let's see if there's any other path. I can go from 3 to 1. Okay, 3 to 1 is 50. And then 1 to 3. But 1 to 3 is infinity. So basically, I cannot go. Right? So we'll do this for 4 also. 4 to 1 is infinity. Can I go? This is also infinity. So this is not changing. 4 to 2 is infinity. Can I go 4 to 1? But that is also infinity. So this is not changing. 4 to 3 is 60. Can I go from 4 to 1? But this is infinity, right? So this will remain minimum value. So it will remain 60. Final, this diagonal, you don't have to solve it. It'll be the same value, right? So after doing D1, right, our adjacency matrix has changed. Earlier, this was infinity. Now this is 60, right? So going forward, now we finished one iteration of K, right? We are doing the second iteration of K, where we are taking K as 2. But to do this, we will be referring to the adjacency matrix, what we computed in the last run, right? It is D1, what we computed. It is not D0. It is not the original adjacency matrix. It is the computed adjacency matrix. This is what we also said in dynamic programming, right? We will use the solved solution, or we will use the solution which we solved in the previous step. So it is D1. That's something I wanted to highlight. So we will take this as our adjacency matrix now. So it is the same thing. I think only 60 has changed. This has changed. This is 60. So this is my D1. Okay. So now for all other purposes, while computing D2, I have to look at this matrix. Okay. So let's solve this. Okay, so let's solve this. So that's one thing I wanted to highlight. So when you go to K equals 2, you have to use D1. Okay, but now let us split this. So let's open it up and write. So it says you can go from 1 to 1, or you can go to some intermediate vertex and then go to 1. And in our case, we know intermediate vertex is now we are trying with 2. Okay, so you can either go directly or you can go to intermediate vertex and then go here. I'll just write it down. 1 to 3 directly, or you can go to intermediate vertex and from there to 3. Okay. So this is for 2 to 1 directly, or I can go to 2 and from there I can go to 1. This is 2 to 2 directly. 2 to 3 is direct, or I'll go via intermediate vertex. 2, 4. Let's solve this also. Okay, let's try to solve this. Like we said, now to solve this, we will use the D1 matrix, right? So see, these values will be same. So I'm going to skip all of this. Okay. So this I'm not even calculating. I know it will be same. Let's try for 1 to 2. You can um, 1 to 2 is 10. You can go from 1 to 2, 10, and 2 to 2 is anyway 0. So it's the same value. 1 to 3 is infinity. But can you go to 1 to 2? Yeah, 1 to 2 is 10. And from there, 2 to 3. 2 to 3 is infinity. So it's not changing. Let's try this. 1 to 4 is 40. Can I go 1 to 2, which is 10? And from there, 2 to 4. 2 to 4 is 20. Yeah. Take a look at this one. You're seeing some changed value here, right? Right. So if you, yeah. So if you take a look at this, in your original value, 1 to 4 was 40. Okay. But there's an alternate path where you go 1 to 2 and 2 to 4. So 1 to 4 is 40. But you have an alternate path, YR2, right? So 1 to 2 takes 10 and 2 to 4 is taking 20. So if you see here, this overall cost is lesser than this. So we need the minimum, right? So although the path is there, we will be changing this to the minimum path, right? So this has changed. So it's not just about finding wherever it is infinity, even the numbered value, if it is minimum, it will change. Okay, let's try this. 2 to 1 is infinity. 2 to 2, I'm not changing, I'm skipping. It will be the same. Let's try for 2 to 3. 2 to 3 is infinity, but can I go from 0 to 3 is again infinity. This is also not changing. 2 to 4. 2 to 4 is 20. Can I go from, it's the same thing, right? 20. 3 to 1 is 50. Can I go from 3 to 2, which is 60, and 2 to 1? 2 to 1 is anyways infinity. So this value is minimum. It will stay. Let's try this. 3 to 2 is 60. Is again 3 to 2 plus 2 to 2. It's going to be the same. 3 to 3 is 0. I'm skipping this. 3 to 4 is infinity. But can you go from 3 to 2, which is 60, and then 2 to 4? So 2 to 4 is 20. Okay. So again, take a look at this one. Right. So 3 to 4, we said initially there is no path from 3 to 4. It is infinity. However, we found an alternate path. Look at this. So initially we said there is no direct path from 3 to 4. This is not there. This is infinity. However, you can go from 3 to 2 as between and then reach it. So this cost us 60. This is 20, which is 80, right? We found an alternate path here. So now this changes from infinity, it becomes 80. This has changed, right? Let's solve the last piece. 4 to 1 is infinity. 4 to 2 is also infinity, so this will not change. 4 to 2 is infinity, or this is also infinity. Okay. 4 to 4, 4 to 3 is 60, but can you go to 4 to 2? This is infinity, so this will stay, and this is also 0. Okay, so we have completed D2. So after D2, we see this is the new matrix. So let me copy this. Because now to solve D3, I will use D2. So I need this. Right? I need this. Just 30. Okay. So I'll say here D3. So this means K is in middle. So what does this mean? I can have 1 to 1, or I can go 3 in between and go to 1. That's what here is. So here k is 3. So I can go directly, or I can go to this. So 3. 3 is my intermediate matrix, and from there go to 1. I'll expand this. If I'm going wrong somewhere, please correct. One second. Okay. Okay. Let's see if something changes now, because still we see there are some infinities, right? Let's see if solving this will help get a path there. So now I'm going to skip these diagonal ones, okay? So I'm going to skip this 2 to 2, 3 to 3. You don't have to do 4 to 4 also. You don't have to do. Okay. And now 3 is in middle, right? So if you see here, 3 is in middle, it actually doesn't matter. See, you're already doing 3 to 1, right? So wherever 3 comes, right? And 3 is already here, you can skip those because the values will not change much. So I'm going to skip this wherever the 3 is already. So basically we have I, J, and K, right? But so you need some different value in IJ. Then only it will matter. If your value is same, then it's not going to give you any results. I'm just doing some optimization here. 3 is already here, right? So wherever your actual value contains 3, you can actually skip that. All of this you can skip, right? Here also, if you see 3 to 3, it's actually not changing much, right? Wherever 3 is in IJ, I'm removing that. That's what I'm doing, right? See here, it's the same thing, right? So you can skip this also. And wherever you have 3, you can skip this, right? So we did some optimization. We don't have to solve everything. Wherever k is coming in this brackets, you can actually discard all of that. So you have to solve a lesser number here.
Even for D2 and D1, ma'am?
Yes, D2 and D1 also. I didn't show you this optimization there because I wanted you to understand the first straightforward way. You can actually solve. See, unnecessary, we solved this. If you see here, D is here, what K is 1, right? So wherever K is in your IJ, wherever 1 comes, the value did not change anywhere here. You saw? It is the same thing, right? It is, there's no difference between the second option and the first option, right? It was the same thing. So you can actually skip this. Wherever 1 is there, you can skip this. Here also, wherever 1 is there, you can skip this. And wherever 1 is there, you can skip this. Wherever 1 is there, you can skip this. And also all the diagonals you can skip. Here, all the diagonals you can skip. That means 1, 1, 2, 2, 3, 3, and 4, 4. Right? This way you can do some optimization. Same thing with here. So here your K value was 2, right? So wherever 2 comes in this one, you can skip all of that. You don't have to do all of this. Right? And skip all your diagonals. That means 1, 1, 2, 2, 3, 3, 4, 4. So this will save some time for you. Now, if you see, the original changed values are only between what we didn't scratch, right? See here, we got some changed value here, we got some changed value here. So that way you can optimize. So now we have lesser numbers to solve. Let's do that. So 1 to 2 is 10. We can do 1 to 3. Again, it's infinity, so it will not change. This would remain 10. This will remain 10. 1 to 3 is infinity. Here is again, this we scratch, right? We don't have to do this. Let's do this. 1 to 4 is 30. 1 to 3 is infinity. So this remains, right? 2 to 1 is infinity. Can I go from 2 to 3? But 2 to 3 is also infinity. So not change. All of this we're skipping. We're skipping this, we're skipping this. Let's do this. 2 to 4. 2 to 4 is 20. 2 to 3 is infinity, so 20 remains. Okay. That's on here. Here, see, if you see, nothing we're going to solve. We're skipping all of this. I can directly go to 4. Okay. Here also only 2 I have to solve. 4 to 1 is infinity. Can you go to 4 to 3? Yeah. And from there, 3 to 1. Yeah, this is what 50, I guess. Right? So here we saw some optimal. We found a path. Initially, it was infinity. But if you go via 3, you get a path. You understood that? So this one. We are saying 4 to 1. Initially, it was infinity. But you can go from 4 to 3, 3 to 1. This is possible. So this is 60 and this is 50. So overall cost is 110. Right? So 4 to 1 changes now. From infinity, it becomes 110. Okay. So let's do 4 to 2. 4 to 2 is infinity. Can you go to 4 to 3? Yeah, which is 60. And then 3 to 2. 3 to 2 is 60. Right? Here also. See, initially 4 to 2 was infinity. But you can go from 4 to 3, 3 to 2. Right? So here also we found one solution. Initially it was infinity, but if we found an alternate route. Right? So overall cost is what? This is 60. This is also 60. So it is 120. So now you replace this infinity with 120. Right? That's it. We don't have to solve any of this. So this is your new D2 matrix. Sorry, this is our D. This was our D1. Okay. Sorry, this was D1. I copied it. I did not change this. So we are solving for 2, right? So this becomes our D2 matrix. Then when we copied here, we are actually bringing the D3 matrix. Okay. Now let's do the D4. Last one. First, I'll write it down. So what does D4 here means? K equals 4 and 4 is going to be my there can be A to B some matrix, but I'm trying to find out if via 4 you can go achieve it. Okay, so let's say so here again let us do some optimizations. Diagonal ones I'm not solving, so I'll skip this. I will skip 2 to 2, 3 to 3, 4 to 4. So the diagonals I'm not solving, and wherever 4 is here, that means this I'm not solving, these also as well I'm not solving this. Wherever 4 is in your brackets, right? I'm not solving this because it will be the same. Okay, so now let us, I'll just expand. So you can go 1 to 2, or you can go 1 to 4, 4 to 2. That's it, right? So let me bring in this table down. So this is important. You need to reuse the previous table. And now we are actually solving for D4. Okay, so let's check. 1 to 2. 1 to 2 is 10. Can you go 1 to 4, which is 30? And from there, 4 to 2, which is 120. Obviously, this cost is more, so I will stick to 10. Here, 1 to 3 is infinity. Okay, but can you go 1 to 4, which is 30, and 4 to 3, which is 60, right? So here you got some path, right? Initially, 1 to 3 is infinity, right? But we found an alternate path via 4. Right? So this changes to 90. So this infinity changes to 90. Okay, 2 to 1 is again infinity. Can you go 2 to 4, which is 20, and then 4 to 1, which is 110? Yes, you can do that. So the overall cost is, what is this, 130. So here also this infinity has also changed. It has now become 130. Let's do this. 2 to 3 is again infinity, but can it go from 2 to 4? That's cost is 20, and 4 to 3 cost is 60. Yes, you can do this. So we found one more solution. Right? So we got it as 90. So which this infinity also we saw 80. Sorry. Right? Anything left for us? 3 to 1. 3 to 1 is 15. You can go 3 to 4, which is 80, plus something, but I'm not solving because I know this is minimum, right? Skip this. 3 to 2. 3 to 2 is 60. Can I go 3 to 4? 3 to 4 is 80. It's again, anyways, bigger, so I'm skipping this. That's it, right? We are done. So if you see, this is your final matrix. So I just rewrite the final matrix. After solving this all source shortest path, you got this matrix. Right? So you have 10, 90, 30, 130, 0, 80, 20, 50, 60, 0, 80, 110, 120, 60, 0, right? So if you look at it, there are no more infinities, right? No infinities means From every source, I can go to every other vertex. Like that is also shortest path, right? Let's verify that. All, what is it? All source shortest path. So if 1 is the source, I can go 1 to 1, obviously. I can go 1 to 2, I can go 1 to 3, I can go 1 to 4. Then second, if 2 is my source, I can go 2 to 1, 2 to 3, 2 to 4. If 3 is my source, I can go 3 to 1, 3 to 2, 3 to 3, of course, 3 to 4. And finally, if 4 is my source, I can reach all the vertex. So all source shortest path is found with this. Is this clear?